All right, boys and girls, welcome back to the drive-through, sponsored by the deli. Stop by the deli and get yourself some flux. All right, so this is my attempt to teach you 14.7. You will have no chance of understanding this video if you don't recall the answers to these 4 questions right here. So what is divergence? Okay, divergence came from section 14.1 and 14.2, so we learned about it a long time ago. Divergence dealt with force fields. Okay, we are talking today about 3-dimensional force fields. The divergence was a measure of how the magnitude of these vectors were changing in different places throughout the force field. Okay, does that make sense? So if you can remember the analogy we used back in those videos, we said that if the divergence was 0, that the shapes were just moving along the plane. If the divergence was positive, then the vectors or the shapes were expanding at that point, each vector, and then if the divergence was negative, the vectors were contracting or being squished. So that's what divergence was measuring, how the magnitude of these vectors changed throughout the force field. So you can imagine, like, if you had a space in your force field where it looked like that, the divergence would be positive as you went this way. Does that make sense? Okay. How did we calculate divergence? We integrated the force dot del, and that's just some notation. But remember that we found divergence by dotting it with del as an operator. We'll get to that later in the example. And we found curl by doing what? Crossing it with del as an operator. Okay? And this would be ds. Okay. What did Green's theorem help us accomplish? Green's theorem, go ahead. Exactly. Green's theorem allowed us to calculate a line integral. Well, what the heck's a line integral? Well, remember that one of the things we would use over a line integral would be to find the total work done over a line through a force field, so it's force dot distance. So if we wanted to find the work by adding up all the little force dot distances along those paths, Green's theorem allowed us to do it by simply using an area calculation. So that's the magic of this. We are taking something that is one-dimensional in Green's theorem. We are taking something that's one-dimensional and calculating it by using a 2-dimensional measurement. That's the magic. Okay? And how did we find flux? Flux was just the surface integral of f dot n ds, where s was the surface area. So that's the 4 things you got to understand to follow along with today's video. Okay? Okay, well, the divergence theorem is also called Gauss's theorem. So this thing is totally legit if Gauss figured it out. And so what it tells us is that you can find a surface integral. So we considered this flux. Okay? So you could find the sum of the flow. Let me draw a little picture here of an egg. Flux was calculating mass per second or volume per second of all of the flow that was coming out of or into a surface. Okay? We use surface integrals to do that. This is a surface integral. What Gauss's theorem, or more popularly known as the divergence theorem, allows us to do is equate the sum of the flux, or the net flux, by using volume instead, which is going to be a lot easier for us. Okay? So you can do that by using a triple integral of the divergence of the field dV. Okay? So that is today's theorem. That is the divergence theorem. Okay? So we're going to go right into an example here. Okay, this is example 1 of 1. Let Q be the solid region bounded by the coordinate planes and this plane. So let's graph that. Hopefully this looks familiar to you. We've done a problem similar to this with the same plane. Okay, so it's important to understand that thing is now a solid. It's not just the sail, the triangular sail here in the front. We have already calculated the flux of that sail. What we are calculating is the flux of this solid. And so if we wanted to do it with surface integrals, how many surface integrals would we have to calculate? 4. So that's the whole point of this. We're saving ourselves from having to do that. Does that make sense? Okay, so the easiest way to write your bounds, well here we know that, well here, let me get started with a couple things. We should find f sub x, f sub y, and f sub z. Okay? So that's going to be 1, 2y, and 1. We know that flux, sorry, not flux, we know that divergence is equal to our force dotted with our operator del. Thank you. This should just be an x. So that is going to be 2 plus 2y. Do you see what I did there? That's just a review from 14.2. Basically, you do the derivative, the partial derivative with respect to x, which is 1, plus the partial derivative with respect to y, which is 2y, plus the partial derivative with respect to z, which is 1. Okay? That's kind of a review of how you find divergence. So we're going to integrate over that. It's 1 plus 2y plus 1, and that's 2 plus 2y. Okay? So we're going to use this where it says this. That's what we did so far. We haven't done anything else. Okay? All right, so it may be better notation to write this as m sub x, n sub y, and p sub z. That's probably more accurate to how you learned it. Because you remember, a force field was defined as m, comma, n, comma, p, where those were functions. Okay, just stay with us. We just got some work to do before we even get started on these. The other thing we're going to have to do is come up with our dv. So notice that z equals 6 minus 2x minus 2y. Okay? And then if we found our bounds on x, x goes, let's see, This is the x-axis. Sorry, this is the x-axis. This is the y-axis. So x goes from x equals 0 to this. Well, if you just let z equal 0, you get that level curve. So this curve right here is 2x plus 2y equals 6, that line. And so if you write that in terms of x, you get x equals 3 minus y. Do you understand that? So we know that x, z is going to go from 0 to this. X is going to go from 0 to 3 minus y. And then what's y going to do? Y is just going to go from 0 to 3. So now I think we're ready to set up our triple integral. Okay? Remember that the sum of the surface integrals, f dot n ds, we now write as the triple integral of the divergence of f dv. Okay, so that's the theorem we learned today. That is the divergence theorem. So we know that y goes from 0 to 3, that x goes from 0 to y minus 3. Sorry, thank you, 3 minus y. And z goes from 0 to 6 minus 2x minus 2y. And what we're about ready to do is work this entire thing out by hand, because we can, and we only should once, and we'll feel good when we're done. So if that doesn't interest you, you can stop watching the video. The divergence of f we calculated to be 2 plus 2y, and now we've got dz, dx, dy. Okay? Here we go. So this is the integrals of 2z plus 2yz as z goes from 0 to 6 minus 2x minus 2y dx dy. Okay, so two times 6 minus 2x minus 2y minus 2y times 6 minus 2x minus 2y. Just don't let me make a mistake. Okay? Thank you. That was just a test to see if you were not going to let me make a mistake, and you're passing the test right now. $12 minus 4x minus 4y plus 12y minus 4xy minus 2y squared plus 4y. Are you sure? Minus 4y squared. Yep. Thank you. Dx dy. Got our signs right? Plus, minus, minus, plus, minus, minus. All right, so we can combine just the y's. Is that all we can combine? So I'll kind of do this to make it a little easier on ourselves. 8y, right? That's what we should have there. All right, we're taking the integral with respect to x. So that's 12x minus 2x squared, bless you, plus 8xy minus 2x squared y minus 4xy squared as x goes from 0 to 3 minus y, all with respect to y. I'm sorry, this is wrong. There we go. right? All right, integrate it with, pop in 3 minus y at all places that there is an x. 12 times 3 minus y, I think I'm going to write it out. So that's 36 minus 12y, right? Minus 2x squared. Well, 3 minus y squared is 9 minus 6y plus y squared, right? So if I multiply that by 2, by negative 2, I get negative 18x squared. Sorry, that's a, yep. Negative 18, excuse me, 12 times, no. I'm on this one, got you, I'm looking at the 12. 2 times that is negative 18 plus 12y minus 2y squared, okay, 8x. 8 times 3 minus y, I'm just going to write this, so plus 24 minus 3y minus 8y, and then times a y here, right? I just didn't feel like doing that all in one step. I felt like I'm just going to mess something up. And so minus 4x times y squared. So, okay, sorry. So minus 2x squared. So minus 18 minus 12y plus 2y squared times y, right? And then minus 4x, so minus, this is 4x here, so 12 minus 4y times y squared. And I have a dy over there that you can't see, okay? So it's the integral from 0 to 3. Okay, I'm just going to, these will cancel. 36 minus 18 is 18. So these are gone. And then I'm going to write everything else out, okay? Minus 2y squared plus 24y minus 8y squared minus 18y plus 12y squared minus 2y cubed minus 12y squared plus 4y cubed dy. Integral from 0 to 3. Okay, so okay, that pretty much keeps them straight for me. So I'm going to just go in reverse order here. 18 plus 6y. Do you guys agree that it's 10y, a negative 10y squared? Nice. All right, almost there. 18y plus 6y squared over 2 minus y to the fourth over 2, right? as y goes from 0 to 3. So 18 times 3 is 54 plus 27 minus 90. Is that right? Is that 81 over 2? No, is that the next one? 243 over 2? 3, 9, 27, 81. Right? Is that right? Does it actually add up to it? Yes. So, what the heck did we just find out? Did we multiply by our density at all? So, we did not multiply by a density, so what did we just calculate? Volume. Okay, volume of flow through these 4 surfaces per second. That's what you just figured out. And what is controlling the volume of flow? 2 things. Can you name it? What are the 2 variables that affect the volume of flow? The surface area and the force field. Got it? Can I get a boom? Lex? Boom.